Let us look at and analyze these three particular instances of constraint motion equation and relations. So in the first case, this is the mass m1, this is the mass m2. There is only one single string, so I'm going to assume the distance of mass m1 from the rigid support to be x1. So this part of the string also happens to be of the length x1, this part, and we are going to assume the distance of m2 from the rigid support to be x2. So this distance is x2. So if I were to label them, this is x1, this is also x1, and this is x2. We do not consider the 1/4 circumference that passes over the pulley, because that part, that length of the string when differentiated, is going to churn a zero result for us. So we write down the constraint motion equation as x1 plus x1 plus x2 happens to be the length of the string. On double differentiating, we get 2a1 plus a2 equal to 0. So this simply is our constraint motion relation, which relates the two accelerations a1 and a2. Here we will need to consider the direction of acceleration of m1 to be towards the left hand side. I am going to assume that away going sense is the positive sense, so m1 has to go away from the rigid support, m2 is going below. So this is the direction in which I have assumed the accelerations a1 and a2 to be. So for writing down the equations, we need to understand that since it's one and the same string, the tension in this string is going to be T. For the block M1, the Newton equation in the horizontal direction happens to be minus 2T, because minus 2T is the force that is acting in the positive direction of acceleration. So even if it is counterintuitive, even if we get a negative result for A1, no problem is there. It simply means that we have assumed A1 to be towards the left, and A1 actually takes place or happens to be towards the right. So minus 2T is equal to M1 A1. For the mass M2, we get to write M2G minus T is equal to M2 A2. So these are the two constraint motion equations that we have to use. In the second case, let me label the masses. So this is the mass m1, this is the mass m2, and this is the mass m3. Let's note down the constrained motion, rather constrained lengths that we are going to use while adopting constrained motion. So this is, let's say, the distance x1. This is the distance. This is the distance x2. Let me take x2 from the rigid support. This is the distance x2. This also happens to be the distance x2, and this is the distance x3. So you might have noticed that I have taken x2 to be till pulley P2 only. This is okay in this case because M2 is rigidly connected to the pulley P2. That means m2 is not moving with respect to the pulley p2. That also implies that the acceleration of p2 is going to be the same as the acceleration of mass m2. So this happens to be x1, this happens to be x2, this happens to be x2, and this happens to be x3. The tension in the string is T, T, T and T because it is one and the same string. So in such a case, I can write down the constraint motion equation as x1 plus 2x2 plus x3 is equal to the length of the string. Double differentiating, we get a1 plus 2a2 plus a3 is equal to 0. So this is one equation, which is the constraint motion equation. Now for the other two equations, for the mass m1, we have to assume that the acceleration is in the leftward direction. So the acceleration over here for mass m1 is in the leftward direction. This is a1. For mass m2, a2 is down below, and for mass m3, a3 is down below as well. So for the mass m1, we may write down the equation minus t is equal to m1 a1. For m2, we can write down the equation m2g minus 2t is equal to m2 a2. For m3, we can write down m3g minus t is equal to m3 a3. So these are the equations that will give us the correct answer for a1, a2, a3 and t. 4 equations, 4 unknowns. This is the mass m1 in the third case. The small mass happens to be m1 and the larger mass happens to be m2. So here this system will not move unless there is a force applied. So there is a force that is applied towards the right hand side, and this force happens to be F. This F force is applied. Now let us assume the distance of m1 from the rigid support to be x1. So this much distance is x1, and the distance of m2 from the rigid support to be x2. This pulley is rigidly connected to the mass m2. So the motion of the pulley and the acceleration of the pulley is going to be the same as the motion and acceleration of the mass m2 because they are rigidly connected. The tension in the string is assumed to be T, so the tension in this string happens to be 2T. Let us now analyze both the blocks. So in order to deploy the constraint motion equations over here, we'll have to understand that this much length is effectively scaling as x2. So this part of the string is scaling as x2, and this part of the string is scaling as x2 minus x1. This much part of the string is nothing but x2 minus x1. This part of the string is x2 minus x1. So we can here write down the constraint motion equation as x2, which is the upper part of the string, plus x2 minus x1 is equal to the length of the string. On double differentiating, we get 2a2 minus a1 is equal to 0. So this happens to be the constraint motion equation. Now in order to get the Newtonian dynamical equations, we simply have to do the analysis of mass m1. Now we should take the accelerations to be going away from the rigid support. So for the mass m1, the acceleration will be a1 over here, and for the mass m2, the acceleration will be a2 over here. You could have taken both the accelerations to be going towards the rigid support as well. We just need to be consistent while solving the particular equation. So all the accelerations will be going away from the rigid support, or all the accelerations will be coming towards the rigid support. Here for mass m1, we could write down T as the only horizontal force that is acting towards the right hand side. So T is equal to m1 a1, and F minus 2t. This is the net rightward horizontal force of the mass m2. F minus 2t happens to be equal to m2 a2. Considering these three equations and the three unknowns a1, a2 and t, we can solve this above mentioned system. Now next are two particularly interesting and cute questions. So basically let's understand the first question. This is the mass m1, this is the mass m3, and this is the mass m2. They are connected via one single string as shown, that runs like this, connecting all the three masses. So assuming this particular distance to be x1, this also happens to be x1. Assuming this particular distance to be x3, this also happens to be x3. Interesting part to note over here is the fact that this much part, which is the distance between the two fixed rigid pulleys, this much part of the length of the string is always constant and it is not moving. This is an interesting fact to note over here. X2 is simply assumed as this length. This length happens to be x2. So now labeling them all, this is x2. So we are effectively measuring all distances from a rigid support. So this is the particular rigid support that we are using in order to measure all distances, this rigid support. So this is x2, these two are x3, and these two happen to be x1. So the length of the string can be written down as 2x1 plus x3 plus x3 minus d. So how come this has happened? So this is x3, this whole thing is x3, this whole thing is x3. So this much part of the length of the string is x3 minus d, wherein d is this small length, that is the length between the two pulleys, the length of the string between the two pulleys, that happens to be constant in this particular case, plus 2x2. So this happens to be the length of the string L. So on double differentiating, we get 2a1 plus 2a2 plus 2a3 equal to 0. This implies a1 plus a2 plus a3 is equal to 0. So this is one of the constraint motion equations, one of the equations that will be used to solve this particular system. It's the same string, that's why the tension in the string is going to be equal to T. On the mass m1, 2t is acting towards the right hand side, but we are going to assume the acceleration of mass m1 to be towards the left hand side. So a1 is assumed to be towards the left hand side, a3 is assumed to be towards the right hand side, and a2 is assumed to be down below. So we have to assume all accelerations to be going away from the rigid support or coming towards the rigid support, all of them. So here in this case we have assumed all of them are going away from the rigid support. So for the mass m1 I can write down minus 2t is equal to m1 a1. For the mass m3 I can similarly write down minus 2t is equal to m3 a3. For the mass m2 I can write down m2g minus 2t is equal to m2 a2. So these are the four equations that can be used to solve for a1, a2, a3 and t. Now in the next particular illustrated example, this is the mass m1, this is the mass m2, and this is the hanging mass m3. So these two masses m1 and m2 are kept on a frictionless table, and they are connected via a horizontal pulley that is kept on the table as shown. So this is the horizontal pulley kept on the table. Now over this pulley passes a string. Let's say the length of the string is L1. Let's assume that the length of the string is L1. The tension in the string L1 is assumed to be T. So here the tension is going to be 2T. This particular string passes over the pulley that is connected on the edge of the surface, and this string is attached to the mass m3. So this is the particular given situation. In this situation, let us assume the distances of x1, x2 and x3 as like this. So this is the distance x1. I'll find a better location to draw it. So this is x1, this is x2, distance of m2 from the rigid support, and this happens to be x3. Alright, now we also need to take into account the fact that the pulley is also moving, and this I'll label the pulley as P1 and the distance of the pulley as xp1 from the rigid support. So this is x1, this is x2, this is xp1 and this is x3. Now in order to write down the constraint motion equations, we understand that this much part of the length of the string happens to be x1 minus xp1, and this much part of the length of the string L1 happens to be x2 minus xp1. So we can write down x1 minus xp1 plus x2 minus xp1. So these are the two segments of the string L1. So this happens to be the length of the string L1. On double differentiating, we get A1 plus A2 minus 2 AP1 is equal to 0. For the string L2, it is pretty obvious that xp1 plus x3 is the length of string L2. So xp1 plus x3 is equal to L2. On double differentiating, we get AP1 plus A3 is equal to 0. Multiplying, this equation with 2 and adding it to the first equation, we get a1 plus a2 plus 2a3 is equal to 0. So this happens to be the constrained motion relation. Now we need to write down the Newtonian dynamical equations. So for this, we'll assume a1 to be in this direction, a2 to be in this direction, and a3 to be in the downward direction. So this happens to be a1, this happens to be a2, and this happens to be a3. So we can write down minus t is equal to m1a1 minus t also happens to be equal to m2 a2, and for the mass m3 we can write down m3g minus 2t happens to be equal to m3 a3. These are the three equations that are going to be used for solving this particular system. Here we can see that a1 happens to be equal to a2, so that is a coincidence, but that can also be explained via physical intuition because there is no gravity acting against the masses m1 and m2, and that's the reason why their acceleration happens to be the same. So with evolved physical intuition, the student of physics will be able to understand this particular aspect of this particular problem. So these were few important examples of constrained motion systems that we saw. These three and these two over here. I urge the student to earnestly study them. They are going to be useful and helpful.